Cool. Well, welcome, good morning, and apologies for not being there in person, and I just lost my slides. So, okay, can you see the slide, Ken? No. As long as I don't hear anything, I assume it's a yes. So, pleasure to be here, even though not in person, and thanks for getting up early to listen to this. It's 4 years since I last gave a talk at FOSDEM, and at that time, seL4 had just been open source, and a lot has happened in the meantime. So I'll give you a bit of an update, and in the end, talk about where the community is at. So this thing represents one of the more exciting things that has happened with seL4.
Yeah.
This is a, yeah.
We don't see your slides. Is this intended?
No, it's not. Oh, God. Okay.
Maybe you may toggle back to full screen. I think it was full screen.
Okay, for some reason stop sharing. I'll share again. Your screen sharing.
Yeah, now we see it.
You should see something.
Yeah.
And
so
now you should see the slide.
Yeah, fine.
Full screen.
Yeah. So I deactivate my microphone again. Okay?
Yeah. Okay. So this is one of the things that happened recently. What you see here is a Boeing helicopter flying, and it's not just flying, it's flying autonomously. There's a pilot on board for safety reasons because they don't get FAA approval to flying it without, but it's actually flying totally autonomously. This is around Arizona, and of course the exciting thing about it, it's flying on seL4. What's even more interesting is some of the history here. So this is a military-grade system. It's actually a defense system. And you should think it's reasonably secure. But it turns out that professional pen testers took about 2 weeks to completely audit it. And they could completely control the flight. They could have crashed it or diverted it or whatever. And this was the starting point in the DARPA HACMS program, which ran for about 5 years, finished about a year ago. And what we did with our colleagues there is convert the system to seL4 and make it secure. So in total, there were 4 vehicles. There were 2 ground vehicles and 2 air vehicles. Each of them had a research platform, like this drone, where we ripped out all the electronics and replaced all the software. And this US Army robotics reference platform, and then the military vehicles, which is this Boeing autonomous helicopter and autonomous trucks. And what we did with our partners were retrofitting these systems for security by putting them on seL4 and doing some re-architecting of the system. And in the end, we kept the hackers out. There was a demo where they did a in-flight attack that in the past would have completely compromised the system, and it was completely protected. Specifically, we gave them root access to a virtual machine running Linux on the system. The original system had everything running on Linux, and the attacker could completely compromise the Linux VM, but it couldn't break out and affect the rest of the system. So that's so much as motivation. A rough outline of my talk is quick intro to seL4, a technical update on a number of the things that happened in the last few years, and this is the bulk of the talk, and then at the end I'll talk about the status of the community and the whole ecosystem. So for those who haven't heard about seL4, it's a microkernel, and it's arguably the world's most secure and safe operating system. What is particularly unique about it, it has probable security enforcement, and I'll talk about on the next slide what that means. It's also, at least as far as the open literature is concerned, the only protected mode operating system with a complete and sound analysis of worst case timing behavior, so that's the prerequisite for doing hard real-time. And in particular mixed criticality real-time, where there's trusted and untrusted components. Besides all that, it's the world's fastest microkernel. We never compromise with performance. And of course, that's the reason I'm here. It's open source, and it's been open source about 4.5 years ago. So the security story is summarized in this slide, where I say proof here. This means formal mathematical proof that is checked by that is machine checked. So we have high-level security properties, confidentiality, integrity, and availability enforcement. And we have proof that an abstract model of the kernel, which is formulated in a mathematical logic, is able to enforce these security properties. And then we have further proof that the C code that implements the kernel is what's called a refinement of this abstract model. So it's correct implementation of this model. So that specifically this means under the semantics of the C language, the kernel cannot behave in a way that's not captured by the model. And then there's a further step that shows that the binary code that runs on the actual silicon is a correct translation of the C. So that means that we don't have to trust the C compiler. We can just use standard untrusted and untrustworthy GCC to compile and then run the toolchain that says, yes, the translation is correct. For truth in advertising, there's a few exclusions. All are work in progress. We're working on fixing all of them. Kernel initialization is not verified. Some privileged state, in particular MMUs, are not yet verified at the same degree of detail as everything else. That's very close to being fixed. We have a high-performance multi-core version that's not verified, and we don't have any verification story about timing channels at the moment. Like any high security-oriented operating system, seL4 uses capabilities as to represent access rights in the system. And so these are basically opaque pointers that reference an object and rights conveyed to it. And any kernel operation you try to invoke needs to be authorized by having such a capability. So these are capabilities in the classical object capability form as the computing literature has known them for 40 years. They're quite different from what the Linux folks call capabilities, which are capabilities and, oh shit, I just stuffed up. Accidentally hit. Okay, I accidentally hit the power cord. Okay. Okay, I just need, I think. Okay. Hopefully you can see the slides again, full screen. If not, please, yeah. Okay, good. Okay. So this is the very high level core view of seL4. There's much more to it. In particular, its resource management model, which is quite unique. But that's all established. So I'll give you now a summary of recent things we've done with it. And one of the most significant ones is support for mixed criticality real-time scheduling. What does that mean? So in many particular cyber-physical systems, any sort of hard real-time system where you have non-trivial complexity, you have this integration challenge of mixed criticality, that some components are highly critical and you need to be sure that they operate correctly under all circumstances. And then there's untrustworthy components. So a very high abstracted view of this UAV has a control loop, which is highly critical because that's what keeps the thing flying and stops it from crashing. And then there's other components. For example, there's networks. And so there's a network driver that talks to the ground station, for example, or other communication. And obviously, that one is not critical. If the communication stops working, then the thing will just fly to an endpoint, to a waypoint, probably has some fail-safe logic to fly home or something. The challenge here is the control loop is really slow. It runs of the order, it runs on human time scale, so order of 10 to 100 hertz. The network driver, of course, is really fast. Networks like to be serviced within sort of microsecond time scales. And that means that this network driver needs to be able to interrupt the control loop. It just can't wait for the control loop to finish its 20 millisecond execution because it loses a lot of network packets. So you have to be able for these less critical components to preempt the critical ones, but still guarantee enough time for the critical component to do its job for the safety of the overall system. So that's the core idea of mixed criticality systems. What makes it challenging is that there's sharing involved. So typically in our UAV, there's the vehicle control. It tells the vehicle where to fly to, so it has to access waypoints. These waypoints, they get updated by the navigation system, for example, based on what the video processing tells the system, or updated from the ground station. And so the trusted and less trusted parts share this critical data. And the vehicle control needs to be able to access data that is consistent even while the navigation system may update it. And you need to do that on the same system. A simple way to implement something like that is by what's called a resource server. So we have the two components that use this waypoint data to control the critical control loop and the less critical navigation system. And the waypoint data is encapsulated in a server, which can be invoked from those clients. The navigation system might invoke the client to update waypoints, and the control system may invoke the server to read the waypoints. So that's all fine. As long as the server is simple enough and fast enough, that may be not a big deal. The problem is, particularly if the server has some longer running operations, then we need to count the time properly, because otherwise the navigation system, which, as I argued before, might be running at higher priority, can just DOS the critical system by sending lots of requests to the server. So we need to ensure that time is accounted properly. And in the new version of seL4, we use capabilities, like for every access control in the system, we introduce capabilities for the right to use processor time. So a classical thread will have a priority and a time slice. In the new seL4, we have a priority and a scheduling context capability, which is this capability to a scheduling object, which is encapsulates the right to access the CPU. So it has a period and a budget, and the semantics is that over any time t, you cannot use more than C of the processor. So the ratio of C to T is the bandwidth of CPU this processor is allowed to consume. And there can be, for example, short terms one, so in this case, in 3 time units, it may use up to 2, so 2/3 of the bandwidth, or something that runs for longer time, like our control loop has, in 1,000 time units, it's allowed to use 250. And if things are right, you can see that you can combine those and you'll both get that time. The system, the whole point is the system enforces that something is not allowed to run over its budget, and that way we can guarantee time to lower priority processes, which is exactly what we need for these mixed criticality systems. So, and the way this is done is by being able to borrow scheduling context. So in the case of our resource server, if a client invokes the server, it passes along its scheduling context. The server is then running on the client's scheduling context, and the server time gets charged to the client. When the server finishes its job, the scheduling context returns to the client, and it now has the server time charged to it, and therefore we can prevent this client to DOS the server and force something else to miss its deadline. There's a paper, was in Eurosys last year, And together, this makes seL4 the first ever real-time system with capabilities for time. There's concurrent work at George Washington University, but there hasn't been a system like that before. So the first time we integrated CPU time with a capability system. Second thing I want to talk about is what we call security enforcement by architecture, and this is what's being used on this Boeing helicopter. The idea here is that in seL4, like other microkernels, they have a very low-level interface. seL4 is particularly low-level. And you need to deal with a lot of these objects and capabilities in order to do anything. This here is a representation of the second most trivial example you can build on seL4. So the most trivial one would be a hello world program that just says hello world and then stops. The second most trivial thing is you have two processes and they communicate by sending messages between each other. And just to represent this really trivial example, we have over 50 kernel objects that we need to worry about. And that's just for this trivial example. This is a simple system, but no longer quite as trivial. Each point represents an object and a capability, and you can see there's hundreds if not thousands of them just for a relatively simple system. So that's not a good abstraction level to reason about in the system. So instead, we have a component middleware called CAmkES. That's not particularly unique. For example, Gnode is in many ways much more general component middleware. But CAmkES has some assurance story which you don't get with others. So in this case, we have, in this CAmkES world, we have components that are represented by boxes and connectors that are represented by lines between those boxes. And there's three different types depending on whether you have synchronous message passing, semaphore-like signaling, or shared data. And sort of the top two boxes and the RPC connector in between basically represents this second most trivial example I talked about before. So a much more high-level representation. And the beauty of this in this CAmkES system is that we can provably reason about the system behavior on this CAmkES representation, and it gets correctly mapped onto seL4. So the way this happens is, I'll demonstrate that this example. This is a highly abstracted view of our UAV architecture, and it has some untrusted stuff in a Linux virtual machine. And one of the core security properties of the system is that Linux is only able to talk to the rest of the system by using encrypted traffic, so only via this crypto library. And we can do that by saying, okay, it's not connected to anything else in the system except this one line that goes to crypto. Therefore, we know that if we can trust this crypto component, then we can assure that Linux can't interfere with the rest of the system. So this is our highly simplified CAmkES view of the system. And in order to build the actual system, of course, we have implementations of these components. So each of these boxes has a implementation that's typically in C. So there's a driver, multiple drivers, the virtual machine, etc. And of course, that gets all compiled and linked together. What is missing here is the so-called glue code, which is the operating system calls that enable these communications, so where they do the message passing specifically. And what this glue code needs to look like is completely specified by this architecture view. So we can generate this glue code, which is, again, that's not particularly new. That's what any IDL compiler does. They've been around for centuries. But in our case, we have proof that the glue code that's generated is correct in the sense that if you invoke a function in a component, then this is semantically equivalent to just directly invoking this function in the same address space. So that's sort of a very strong correctness property of this glue code. What we also get is from this CAmkES representation, we can generate the low-level seL4 representation, so in terms of seL4 objects and capabilities. that's represented in a formalism called CAPDL, for Capability Description Language. And again, we generate this automatically from the CAmkES view, and again, this generation is provably correct. And that means when we have the system in this low level, if this low level diagram represents the actual seL4 system, then we know that we can reason about the system according to this high level diagram by these boxes and lines represented in the CAmkES formulas. And the final step is, how do we get the system in this state? We also generate the initialization code that gets the system into that shape. So we have a automatically generated code, which is the init task in the system, which will create all these objects, distributed capabilities, and then we know the system is in a state that's correctly represented by this CAmkES representation on top. And that means we can now do all the reasoning about the properties of the system in this CAmkES formulation. With some limitations at the moment, not all the proof stories are complete yet, but this is ongoing work that's funded by another DARPA program, and it will be finished within the next few years. And if you're interested, there was an article in Communication of the ACM just last October that describes all that. And then there's also tools where this gets tied to a formalism called Architecture Analysis and Description Language, which is an international standard, and that's used a lot in the avionics industry, and there's Eclipse-based tools, etc., the whole language is designed for doing safety cases, and there's analysis tools and all that stuff, and you can use that framework and generate the CAmkES representation from that one, although that generation is not provably correct, and it's unlikely to happen in the near future. And these tools are provided by what we'll call in seL open source. So that was the second thing that's sort of relevant for seL4 in recent developments. And the third one is, okay, we have a verified kernel, but of course, the whole system is more than a kernel. Even the trusted computing base of the system is much more than a kernel. So typically, you have some critical components. There may be some devices where you need to trust the drivers. You may need to have a trusted file system. You have your control code, etc. And all these, if they need to be trusted, ideally they really should be verified. And of course, 11 person years was what we invested in verifying the kernel. All these components of the order of 1,000 to tens of thousands of lines of code. And 11 person years for 10,000 lines of code, and it scales quadratically. That doesn't sound like a particularly attractive way of doing things. It was okay for the kernel, but for doing things on top, you want better productivity. And this is why we're developing the Cogent framework. So Cogent stands for Code and Proof Cogeneration, and it is a language framework for building high assurance components on top of seL4. And it is a programming language. It's a functional programming language that's type and memory safe, but not managed. And it's got a linear type system. Think Rust. It's very similar to Rust in many ways. But unlike Rust, it's got a formally well-defined semantics, and we compile it into C, which is not particularly exciting. But the more interesting part is when we compile it to C, the compiler spits out proof that the C is correct against a component spec, which the compiler also generates. And then we know, okay, we have a correct implementation translation of this Cogent into C, which means that as long as we trust the compiler at least, can reason about the correctness of our code at the level of the Cogent semantics, and we know that the C translation will maintain that semantics. Like Rust, the language is restricted, that you can't program everything in it. It's intentionally too incomplete, so we need to complement it with abstract data types. So these are things like for file systems, we have abstract data types for implementing red flag trees, etc. And the idea is these need to be manually verified. So in the end, you have an overall high-level abstract specification of the complete functionality of this component. You have these abstract data types, which can be verified independently, and the idea is they're highly reusable. And then you're left manually verifying the Cogent code, which is much easier than verifying C code because of the properties of the Cogent language, the fact that it's type and memory safe, that it's purely functional. And so that's the key for increasing the productivity of verification. And we've done some case studies, a number of file systems. There's a paper out there that's about 3 years old now that describes it. And what we found is that, okay, the productivity story is not too bad. So we get a cost per of verified code in terms of dollars per line of code. That's about a factor of 2 less than what our cost was for seL4. Now the cost for the complete verification story for seL4 was about 3 or 4 times as expensive as the earlier Pistachio microkernel, which was an earlier L4 microkernel that was developed in a very similar context by people, university folks who sort of had experience with microkernels, etc. So it's quite a comparable system. So seL4, with its complete verification, was about a factor of 4 more expensive than this earlier system that had no verification story at all. So that means if we get the cost down by a factor of 2, we are competitive with non-assured traditional engineered code. And it seems like with our Cogent approach, we already got half of that gap. We got a factor of 2. And the fact that the reason it's not more has a lot to do with the way Cogent, the initial version of Cogent was done. It was really restrictive. You were forced to do a lot of boring, repetitive stuff, etc. And this is what we're working on at the moment. And so with the ultimate game of having something that really allows you to write systems components and verify them at a cost that's comparable to classical unverified C code. So another interesting aspect is that, okay, when you have this Cogent implementation, presumably, ideally, you want to verify that, but you can actually play a trade-off of dependability versus cost. We could, for example, say, okay, it's a safe language, and therefore that reduces the number of bugs already significantly, and maybe for something that's not ultra-critical, that might actually be enough. And then you have, you just need to write the code, and you have already code that you know is going to be better than the equivalent C code if it was manually written. And then you can do automatic testing, in particular this called property-based testing, which is something that comes out of the Haskell world, where you have a formal specification of your functionality and it generates test cases automatically from that. And in particular, it exercises the interesting bits, so corner cases, etc. And that has been, turns out, is a very effective tool for getting code pretty much correct very quickly. And then, of course, you can do model checking. And then finally, you can do the full functional correctness proof by theorem proving, as we've done it with seL4. So there's a hierarchy of increasing assurance, but also increasing cost, and you can pick your point. But one of the interesting aspects of that is that this property-based testing has an interesting compatibility with our full functional correctness proofs, in the sense that it requires a formal specification. And a formal specification can be reused with the full functional correctness proof. So that means you can use quick checking for properties-based testing for actually developing and debugging your spec, because specs have bugs as well. And it's much easier to verify against a correct spec than an incorrect one, because any bug in the spec will send you down some rat hole, which you need to dig out after a while. So starting with a more or less correct spec is a big win. But also verifying correct code is much easier than verifying buggy code. And so eliminating most of the bugs with property-based testing before you start verification also reduces cost. So there's a whole bunch of trade-offs that can be played, and this is all only at the beginning. But we've already made a lot of progress in the last 2 years, particularly over the last year, in increasing the expressiveness of the language to make it easier to use, reduce the number of lines of code you need to write for implementing some functionality. We put in some of this boilerplate code into syntactic sugar in the language, and we are applying it to other components. So in the past, we used it for implementing file systems. We're now starting to use Cogent for device drivers and network stacks. And that's, by the way, all supported by industry funding. So quite happy to see that there's a fair amount of interest in industry for using this technology. But one particular application area is autonomous cars. So this has nothing to do with DARPA. It's a California-based company doing autonomous driving kits. And they're working with us for using this Cogent technology to get some of their critical components verified. So they have fairly grunty system with 4 ARM8 cores that run the machine learning and sensor fusion and all that stuff. And then they have, and that's running in a SMP Linux. And then underneath it, there's seL4, and then the critical components are pulled out running natively on seL4. And with a minimal trusted computing base, with the idea of verifying that trusted computing base, in particular, writing the drivers in Cogent and verifying them. And of course, the system has redundancy as well. So this is some of the, I think, relatively exciting developments that have been happening around or are happening around seL4. It's sort of, I guess the main takeaway here is seL4 really is the cutting edge of operating system design and development. It's really driving innovation, and there's more and more deployments that help us supporting real-world cases and driving innovation further. Okay, now to what many of you folks are probably quite interested is sort of what's the story about the ecosystem and the general seL4 community. And there's some good and some bad news. So the good news is the community is growing. The developer mailing list is very active. There's heavy support from the US government. They set up a US seL4 Center of Excellence, which is basically an organization where companies can go and get help with developing systems on top of seL4. Obviously, DARPA does that to support particular defense work, but it's not the only defense. There's an seL4-based system has gone through high assurance evaluation, and it's been certified for defense use, and is actually in use in the UK and the Australia defense. But it's also, to me, particularly important aspect is we're getting out of just the defense space into safety critical systems. And this is reflected in the amount of commercial funding we're getting for seL4. So these are companies, some big, some small, some very big, putting real dollar on the table to help us develop the seL4 open source system and the frameworks around it. And pretty much all this work that we take funding for is open source work. Occasionally, we would provide, for example, a proprietary driver for a specific purpose for a customer, but the bulk of the money that comes to us goes straight into developing the open source system, seL4 itself, as well as things that run on top. And it's moving into a number of areas. So there's some of the companies we're talking to are building things for industrial control system to protect them from cyber attacks. Autonomous cars already mentioned, and there's people building frameworks for high assurance medical devices. So a lot of safety critical systems work. So that's the good news. The bad news is really the present state of the ecosystem, which is not where I would really like to see it, and I really thought this would develop faster. At the moment, the whole system is very satanic. You have not a lot of actually usable components, so unlike L4E, for example, which has a fairly mature and rich ecosystem, the seL4 one is still very much in its beginning. There's more components around that people are aware of, but it's poorly documented, hard to find. Some of them are supported, most are not, and this is something we really need to change. There's definitely a shortage of tools, so we would like to see people developing more tools. The Center of Excellence is doing some of that, but we really like to see an open source community doing this. And part of that is really because we have to blame for that. Our community engagement is just insufficient. We're generally very responsive to people putting issues, asking questions on the mailing list, but we're not really proactive. And the main reason is not ill will, it's just we've been too busy. We've been always very stretched with our people. Hiring really good kernel OS developers is hard, and we've been recruiting for years. And with varying success, just recently it's been pretty good. We hired a number of people. But basically just getting enough people in is a bottleneck. And it creates a chicken and egg problem, right? If we can make more use of the community, then obviously that solves part of these problems. But in order to bootstrap that, we need to invest and engage with the community, etc. And we've just been too busy in the past to do that. But that's really changing. So this is a high priority thing for us. We just, over the last 2 months, added 2 full-time OS engineers and a bunch of student casuals. And you will see in the next few months a real change there happening with the way we engage with the community and as it becoming more proactive, etc. The COE is, of course, one important bit of the community because their job is to contribute tools, etc. But we want to have a real sort of open source developer community around that, and we will take steps to help that developing much better. And that includes, of course, on our side, really just documenting much more what's there and use that as a way to encourage community members to just adopt components and support them, etc., and contribute new ones, of course. And part of that, of course, is giving the developer, the contributors, more visibility, etc. So we're working on all of that, and we're open to suggestions. And we're definitely taking steps to improving the transparency of the whole thing. It's been noted a few times that the whole seL4 development is not very transparent, and that's unfortunately true, but we're really changing that. So one step we've already taken, if you're following the developer mailing list, you would have seen that. We started an RFC process. So in future, any major changes will be going through this community consultation process. And it's a way for the community, obviously, to engage as well and make suggestions. So that's already in place. And a few other things that are not yet in place, but we are working on them, is opening up our Jira for kernel and platform issues. That's a bit of a tricky one because there's lots of stuff in there, from some of them 10 years old. Some of the stuff in there refers to projects that are under this.
You have 2 minutes left.
Yeah. Yep, I'm on my last slide.
Okay, fine.
So that needs some cleanup because there's confidential stuff in there and some stuff that could be embarrassing, etc. So that will take a bit to go through, but it's happening. We also created a discourse group, which will be opened up very soon. It already exists, but it's not yet announced, and we'll announce it probably in the next month or so. And there actually is a public roadmap, but it's horribly outdated. About 3 years, we'll update that and be more active in maintaining this. So please talk to us if you're interested, and we really want engaging with the community much better in the future than we have in the past. And that's my last slide. Thank you.
I think we'll try questions and answers. No? 2 minutes.
Yeah. Let me unshare so I can hopefully see.
Yeah. Okay. Any questions? Maybe I try to translate them into microphone.
learn about certified hardware. We have certified compiler, we have a certified operating system. Let's learn about hardware.
Okay. The question is...
yeah, okay, I got that. Certified hardware. Well, it's not our space, right? We are software experts, not hardware experts. Obviously, hardware is the thing that keeps me alive at night, awake at night. We understand how to make software secure. We can't keep, we have no control of the hardware, and we know the hardware is bad. There's a lot of activities happening in that space, particularly around RISC-V, which of course the open architecture encourages that. And there is probably 3 or 4 projects around the world that are working on verifying RISC-V processor implementations, which is really exciting. But it will take a while to get there. But yeah, I mean, you're totally right. Hardware is the big problem. And for example, Spectre and Meltdown demonstrates how dangerous hardware is. So I hope people really get their act together on the hardware side.
Okay. One more. No. Okay. We have to stop here. So thank you for your talk.
Okay. If there's any more questions, send an email.
Yeah. Okay.